There is a boundary in space, beyond which nothing, no information, no light, no signal of any kind can ever reach us. Not because we lack powerful enough telescopes, not because our technology is insufficient, but because the universe itself forbids it. Right now, at this very moment, galaxies are crossing that boundary. Entire cosmic structures containing trillions of stars are slipping beyond an invisible threshold, disappearing from the observable universe forever. Once they cross, no amount of time, not billions of years, not trillions, will ever allow us to see them again. What if I told you that 95% of the universe has already crossed this boundary? What if the cosmos we see represents only a tiny island of reality, surrounded by an infinite ocean we can never observe, never reach, never know? The cosmological horizon is real. It surrounds us, and it's shrinking. Today, we journey through evidence that challenges everything we thought we understood about the scope of existence itself. Prepare yourselves. We begin. In 1929, Edwin Hubble stood at the Mount Wilson Observatory, analyzing light from distant galaxies through the 100-inch Hooker telescope. What he discovered that year would fundamentally reshape our understanding of existence. Every galaxy he observed was moving away from us, every single one. But here's what made it extraordinary. The farther away a galaxy was, the faster it was receding. A galaxy twice as distant wasn't moving away twice as fast. It was moving away at exactly twice the speed, in perfect proportion. Hubble had discovered cosmic expansion. The space between galaxies isn't static. It's stretching, growing, expanding outward in all directions simultaneously. Imagine dots on a balloon's surface as you inflate it. Each dot moves away from every other dot, not because the dots are moving through space, but because space itself is expanding between them. This revelation immediately created a paradox. If space is expanding and distant objects are moving away from us, then objects far enough away must be receding faster than light can travel through space. Einstein's theory says nothing can move through space faster than light. But Einstein's theory says nothing about how fast space itself can expand. The implications are staggering. Consider a galaxy currently 14 billion light-years away, a distance light takes 14 billion years to cross. You might think we could see that galaxy as it appeared 14 billion years ago, shortly after the Big Bang. But here's where reality becomes strange. That galaxy isn't just 14 billion light-years away. During the 14 billion years its light traveled toward us, space itself was expanding, carrying that galaxy even farther away. Today, that same galaxy sits more than 46 billion light-years distant. The light we see tonight left when the galaxy was young and close, but the galaxy itself has been carried to staggering distances by expanding space.
This creates a boundary. Somewhere out there exists a distance beyond which galaxies are receding so fast that their light, despite traveling toward us at maximum cosmic speed, makes no forward progress. Like a runner on an infinite treadmill, the light streams toward us at 300,000 kilometers per second, while space expands in the opposite direction, stretching the distance faster than light can close it. This boundary has a name: the cosmological horizon. Astronomers can calculate its location precisely. The edge of the observable universe currently sits approximately 46.5 billion light-years away in every direction, creating a sphere of observable space roughly 93 billion light-years across. Everything beyond that distance exists in a realm we call the unobservable universe.
But the evidence forces us to confront an uncomfortable possibility. In 1998, two independent research teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, made simultaneous discoveries that would earn them the 2011 Nobel Prize in Physics. They were studying distant supernovae, using these cosmic explosions as standard candles to measure cosmic distances with unprecedented precision. What they found defied every expectation. The expansion of the universe isn't slowing down under the mutual gravitational attraction of all matter, as everyone predicted. It's speeding up. Some unknown force, which physicists label dark energy for lack of a better understanding, is accelerating cosmic expansion. And this acceleration changes everything about the cosmological horizon.
With an accelerating expansion, the cosmological horizon doesn't simply mark where light currently struggles to reach us. It represents an asymptotic boundary that's actively shrinking in terms of which galaxies remain observable to us. Galaxies currently within our observable universe will eventually cross the horizon and vanish forever, disappearing one by one into the unobservable realm beyond. The universe isn't just expanding, it's accelerating into a configuration where more and more of reality becomes permanently inaccessible. But this represents just one piece of a much larger puzzle hidden in the cosmic horizon itself.
The first clear signature of the horizon emerged from the cosmic microwave background, the afterglow of the Big Bang itself. In 2003, NASA's Wilkinson Microwave Anisotropy Probe began mapping this ancient radiation with extraordinary precision. The CMB represents light emitted approximately 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and photons to stream freely through space. That light has been traveling for 13.8 billion years. The matter that emitted it now sits 46 billion light-years away, carried to those distances by cosmic expansion. But here's what the data reveals. we can see structures in the CMB that correspond to regions of space now beyond our horizon. We're observing the baby pictures of cosmic regions we can never see in their present state. Those regions exist right now, somewhere beyond the boundary, but we're forever limited to viewing their infant photographs. Light emitted when the universe was less than 400,000 years old.
The European Space Agency's Planck satellite, which operated from 2009 to 2013, provided even more refined measurements. The data reveals fluctuations in the CMB extending to the edge of the observable universe, showing us structures at the absolute limit of detection. The Sloan Digital Sky Survey has mapped over 1.2 million galaxies across a significant fraction of the observable universe. When astronomers analyze the distribution of these galaxies, they find something remarkable. The patterns show no signs of ending at large scales. Galaxy clusters group into superclusters. Superclusters align along cosmic filaments, vast structures, hundreds of millions of light years long. These filaments connect in a cosmic web of matter surrounding enormous voids. But here's where it gets strange. The largest structures we observe, the Hercules Corona Borealis Great Wall, a cosmic filament spanning approximately 10 billion light years, shouldn't exist according to some cosmological models. Structures this large challenge our understanding of how cosmic expansion should have limited the size of gravitationally bound systems. Recent observations from the Dark Energy Survey reveal that galaxies near the edge of the observable universe show signs of being influenced by gravitational forces from sources we cannot see. Their velocities don't match predictions based solely on visible matter. The data suggests massive structures beyond the horizon, exerting gravitational influence on objects we can observe, like watching leaves blown by winds originating beyond a distant mountain range. Researchers at the Harvard-Smithsonian Center for Astrophysics analyzed the motion of galaxy clusters within a billion light-years of Earth. They found a bulk flow, a large-scale movement of galaxies in a particular direction that exceeds predictions. Something beyond the observable universe appears to be pulling on observable structures. The implications extend beyond simple gravitational effects. In 2019, astronomers using the Hubble Space Telescope and other observatories discovered that the expansion rate of the universe appears different when measured using nearby supernovae versus when calculated from the cosmic microwave background. This Hubble tension suggests either our cosmological models are incomplete or variations in the expansion rate exist at scales approaching or exceeding the horizon. But this represents just one piece of a much larger puzzle hidden beyond the cosmic boundary. The most remarkable discovery involves what happens to galaxies as they approach the cosmological horizon.
Due to cosmic expansion, light from the most distant galaxies becomes increasingly redshifted, stretched to longer wavelengths as it travels through expanding space. The galaxy GNZ11, observed by Hubble, sits approximately 13.4 billion light-years away in look-back time. Its light has been stretched so dramatically that ultraviolet light emitted by its stars reaches us as infrared radiation. But GNZ11 isn't even close to the horizon. Theoretical calculations show that as galaxies approach the true cosmological horizon, their light becomes redshifted toward infinity. The wavelength of their light stretches to cosmic proportions, kilometers long, then millions of kilometers, approaching infinite length as they cross the boundary.
At the horizon itself, time dilation reaches extreme values. An observer watching a galaxy approach the horizon would see that galaxy's time appearing to slow down relative to our own. Events that take seconds in that galaxy would appear to unfold over years, then centuries, then eons to us. As the galaxy crosses the horizon, time there appears to freeze completely from our perspective. But here's the paradox. From the galaxy's perspective, nothing special happens. The inhabitants of that galaxy experience time normally. They cross the horizon without noticing anything unusual, disappearing from our reality while their own reality continues unchanged. The cosmological horizon represents an asymmetry in cosmic information. We lose access to them, but they don't lose access to their future. They simply vanish from all possible detection. Recent theoretical work by physicists at the University of Cambridge reveals something even stranger. The cosmological horizon shares mathematical properties with black hole event horizons. Both represent boundaries beyond which information cannot return to an outside observer. Both involve extreme time dilation at the boundary. Both create situations where, from one perspective, an object appears frozen at the boundary forever, while from another perspective, the object passes through unimpeded. This similarity is not coincidental. In the mathematics of general relativity, both horizons represent null surfaces, boundaries where the paths of light rays become trapped. A beam of light aimed outward from just beyond the cosmological horizon will never reach us, no matter how long we wait. Just as light aimed outward from inside a black hole's event horizon can never escape. The evidence extends beyond classical physics into the realm of quantum mechanics. Stephen Hawking predicted that black hole horizons emit thermal radiation due to quantum effects, particles created from vacuum fluctuations near the event horizon. In 1983, physicist William Unruh demonstrated mathematically that accelerated observers detect thermal radiation from the quantum vacuum, even in otherwise empty space. The cosmological horizon, as a boundary created by accelerated expansion, should also emit thermal radiation according to these quantum field theory calculations. This cosmic Hawking radiation would be extraordinarily faint,
with a temperature billions of times smaller than the cosmic microwave background, but theoretically detectable with sufficiently sensitive instruments.
In 2021, researchers at MIT published calculations suggesting that information lost beyond the cosmological horizon might not be truly lost in a quantum mechanical sense. Just as the black hole information paradox asks where information goes when matter falls into a black hole, we must ask what happens to quantum information about particles and fields that cross the cosmological horizon. The evidence suggests that quantum entanglement, the phenomenon where particles share correlations regardless of distance, might allow information to persist across the horizon in ways classical physics forbids. Particles on our side of the horizon might remain entangled with particles beyond it, creating connections that transcend the boundary itself. The evidence extends beyond observable physics into the realm of fundamental questions about reality.
The scientific framework that explains the cosmological horizon rests on the lambda CDM model, the current standard model of cosmology. Lambda represents dark energy, the mysterious force accelerating cosmic expansion. CDM stands for cold dark matter, the invisible matter that provides gravitational scaffolding for galaxy formation. According to this model, dark energy fills all of space with a constant energy density. As space expands, more dark energy appears, not violating energy conservation, but emerging as an intrinsic property of space itself. This creates a positive feedback loop. Expansion creates more space contains more dark energy accelerates expansion further. The mathematics are elegant and precise. Physicist Alan Guth at MIT developed the theory of cosmic inflation in 1980, proposing that the early universe underwent a period of exponential expansion driven by a similar effect. During inflation, which lasted perhaps 10 to the power of minus 32 seconds, the universe expanded by a factor of at least 10 to the power of 26, growing from subatomic scales to the size of a grapefruit. But here's what matters. If inflation occurred, it suggests that what we call the universe represents merely a tiny patch of a vastly larger reality. The region that inflated to become our observable universe started as a microscopic quantum fluctuation within a much larger inflating space. The true universe, the totality of inflated space, could be exponentially larger than the observable universe. Some calculations suggest factors of 10 to the power of 23 or more. This forces us to reconsider fundamental assumptions about cosmic uniqueness. Andre Linde at Stanford University proposed eternal inflation,
scenario where inflation never completely ends. While inflation stopped in our region of space 13.8 billion years ago, it continues elsewhere, constantly creating new inflating regions. Each region that stops inflating becomes a bubble universe like our own. In this framework, the cosmological horizon doesn't just hide more space like ours. It conceals a potentially infinite cosmic landscape containing innumerable bubble universes, each with potentially different physical properties. Roger Penrose at Oxford has proposed an alternative view called conformal cyclic cosmology, suggesting the universe undergoes infinite cycles of expansion and rebirth. In this model, our cosmological horizon might eventually expand to encompass everything as the universe approaches heat death, at which point conformal geometry allows a new Big Bang to emerge from the infinite future of the previous cycle. Leading cosmologists like Max Tegmark at MIT argue that the cosmological horizon represents the boundary of what he calls a level 1 multiverse, an extension of our observable universe obeying the same physical laws but lying beyond detection. Beyond that, quantum mechanics and cosmic inflation might create higher levels of parallel universes with different physical constants. The philosophical implications are profound. If the unobservable universe is infinite, then quantum mechanics suggests it contains every possible arrangement of matter that could exist. Somewhere beyond the horizon, identical copies of Earth exist. Somewhere further, variants exist where history unfolded differently. The infinite expanse beyond detection contains not just more of what we see, but everything that could possibly exist. Recent breakthroughs suggest we may soon test some of these ideas. The James Webb Telescope, launched in 2021, can observe galaxies approaching within 200 million years of the Big Bang, closer to the cosmological horizon than ever before. Early results have revealed galaxies that appear more massive and more structured than cosmological models predicted at such early times. These observations might indicate that our models of early cosmic evolution are incomplete, or that processes occurring beyond the horizon influenced the formation of structures we can see.
The Nancy Grace Roman Space Telescope, scheduled for launch in 2027, will conduct the largest ever survey of distant galaxies. Its wide field of view will map cosmic structure across billions of light years, potentially revealing how the bulk flow of galaxies responds to invisible influences from beyond the horizon. The Vera C. Rubin Observatory, beginning operations in 2025, will survey the entire southern sky every few nights, creating a time-lapse map of cosmic evolution. By tracking how galaxies move and how structure evolves, astronomers hope to better understand the dark energy driving expansion and pushing matter beyond the horizon. Gravitational wave astronomy offers a revolutionary new window on the cosmos. The LIGO and Virgo observatories detect ripples in space-time from merging black holes and neutron stars. These gravitational waves travel at light speed, meaning they too are limited by the cosmological horizon. But upcoming space-based detectors like LISA, the Laser Interferometer Space Antenna,
will detect lower frequency gravitational waves from supermassive black hole mergers in the early universe. Gravitational waves carry different information than light. They're not absorbed or scattered by matter, providing a clearer view of cosmic history. Theoretically, gravitational waves from events at the edge of the observable universe might encode signatures of influences from beyond the horizon.
What this means for us extends beyond academic cosmology. Understanding the cosmological horizon forces us to confront the limits of knowledge itself. There exist true facts about the universe, about what lies beyond the horizon, about the full extent of reality that we can never verify through observation. Science, which relies on empirical evidence, faces a fundamental boundary. This doesn't render science helpless. We can still use physics to extrapolate, to build theoretical models, to understand the general properties of what might lie beyond. But specific knowledge, which exact galaxies exist beyond the horizon, whether specific structures or civilizations populate that space, remains forever beyond our grasp. Recent developments in quantum information theory suggest one possible loophole. If quantum entanglement truly transcends spatial boundaries, and if entangled particles on opposite sides of the horizon remain correlated, then clever experiments might extract limited information about the unobservable universe through quantum measurements on particles within our observable region. Research groups at Caltech and the Perimeter Institute are exploring these possibilities theoretically, though practical implementations remain far in the future. The most profound implications emerge when we consider our place in this vast, mostly hidden cosmos. The cosmological horizon reveals something fundamental about the structure of reality. The universe we can observe represents an infinitesimal fraction of what exists. If the universe is infinite, and current evidence suggests it might be, then the observable universe represents exactly 0% of total reality. We inhabit a finite island in an infinite ocean, surrounded by a boundary we can never cross, observing only the tiniest sample of existence. Consider what this means. Every photograph taken by every telescope ever built shows us less than a trillionth of the matter in the universe. Every astronomical catalog, every map of cosmic structure, every survey of galaxies documents an infinitesimal fragment of reality. The vast majority of atoms, stars, galaxies, and civilizations exist beyond permanent detection. The most profound implications emerge when we consider consciousness and intelligence. If the universe beyond the horizon is infinite, then it contains infinite instances of every possible arrangement of matter. This includes infinite copies of Earth, infinite versions of human civilization at every possible stage of development, infinite variations on intelligent life in forms we cannot imagine. But we can never know about them. They can never know about us. The cosmological horizon creates infinite, causally disconnected regions of space-time. Each region evolves independently, its inhabitants observing their own finite sphere of reality, surrounded by their own inaccessible beyond. From a cosmic perspective, our observable universe is someone else's unobservable universe. This raises unsolved mysteries about the nature of existence itself. The fine-tuning problem asks why the physical constants of nature, the strength of gravity, the mass of the electron, the cosmological constant, have values that permit complex chemistry and life. Change any of these values by small amounts, and stars cannot form, atoms cannot bond, or the universe collapses or flies apart too quickly for structure to emerge. If the unobservable universe is infinite and varied, containing regions with different physical constants, then our existence in this particular region is not miraculous, it's inevitable. Somewhere in the infinite expanse, conditions must be right for observers like us to emerge. We find ourselves in this particular region because regions with different parameters don't produce observers to ask the question. But this answer generates new paradoxes.
Physicist Max Tegmark points out that if all possible physical configurations exist somewhere, then we should expect to find ourselves in the most common type of universe that supports observers. Some calculations suggest universes slightly different from ours would be more common. This measure problem, determining probabilities in an infinite multiverse, remains unsolved. The cosmological horizon also connects to questions about simulation and reality. If advanced civilizations arise anywhere in the infinite universe, and if such civilizations can create simulated universes, then the number of simulated realities vastly exceeds the number of base-level realities. Statistically, we might be more likely to exist in a simulation than in base reality. But a simulated universe wouldn't have a genuine cosmological horizon. The simulation's boundary would be computational, not physical. So perhaps the very existence of a genuine horizon, a boundary enforced by the speed of light and cosmic expansion, provides evidence that our reality is fundamental rather than simulated.
The ultimate question remains: what lies beyond? Multiple possibilities based on current evidence suggest different futures. If cosmic acceleration continues indefinitely, the observable universe will shrink. In trillions of years, distant galaxies will have crossed the horizon. Eventually, only our local, gravitationally bound group will remain visible. A small cluster of galaxies surrounded by darkness. Civilizations arising in that distant future would observe a universe containing only their local group, with no evidence that external galaxies ever existed. They would be cosmologically alone, their view of cosmic history limited by the accident of when they arose. Alternatively, if dark energy evolves over time, a possibility some observations hint at, the expansion might eventually slow or even reverse. The cosmological horizon could expand, revealing previously hidden galaxies, or collapse, ending in a big crunch. We cannot know which future awaits. We've journeyed from Hubble's initial discovery of cosmic expansion, through the evidence for accelerating expansion and the dark energy driving it, to the implications of a cosmological horizon that hides most of reality from view. The evidence shows us that the observable universe represents a finite sphere, approximately 93 billion light-years across, surrounded by an unobservable realm we can never access. Cosmic acceleration is pushing matter beyond this boundary permanently. The mathematical structure of the horizon resembles black hole event horizons, suggesting deep connections between expansion and gravity. Quantum mechanics hints at possible correlations across the boundary, and the infinite space beyond might contain every possible configuration of matter, including infinite variations on everything we know. Current scientific consensus holds that the lambda CDM model accurately describes cosmic expansion. Dark energy exists as a property of space itself, and the cosmological horizon is a genuine, fundamental boundary on observation. But uncertainties remain about dark energy's nature, the full extent of the universe, and whether anything beyond the horizon can influence our observable region. What began as a simple observation, galaxies moving apart, has led us to contemplate an infinite cosmos mostly hidden from view, a boundary we can never cross, and profound questions about knowledge, existence, and our place in reality. Perhaps the most remarkable aspect of the cosmological horizon is not what it hides, but what it reveals about the human mind. Despite being trapped in a finite observable region, despite facing a permanent boundary on knowledge, we can still use mathematics and physics to understand what lies beyond. We can calculate properties of the unobservable universe, predict its structure, and comprehend our relationship to the vast, hidden reality. The cosmological horizon surrounds us. It limits what we can see, but it does not limit what we can understand. The universe is vast. The mysteries are endless. The journey continues, even if the destination lies forever beyond the horizon.